Artificial intelligence has been widely marketed as the ultimate cost reduction engine. For over a decade, the dominant narrative in both Silicon Valley and enterprise boardrooms has been straightforward: automate tasks, reduce headcount, and increase margins. However, this assumption is now being challenged at the highest levels of the AI industry. A senior executive at NVIDIA has publicly stated that the cost of running AI systems may already exceed the salaries of highly skilled human professionals. This is not a marginal observation, it is a structural signal. At first glance, this claim appears counterintuitive. If AI is more expensive than humans, why are companies accelerating their investments? The answer lies in a fundamental misunderstanding of what AI actually is from an economic perspective. AI is not a digital employee. It is not a substitute for labor in the traditional sense. Instead, it is a form of industrial infrastructure, closer to a factory than a worker. Historically, cost optimization strategies focused on labor arbitrage, outsourcing, automation of repetitive tasks, and process standardization. These strategies relied on the assumption that machines are cheaper than humans at scale. However, modern AI systems, particularly large language models and deep learning architectures, operate under a completely different cost structure. Every interaction with an AI system consumes computational resources. Every query triggers GPU cycles, electricity usage, and data center overhead. This leads to a critical insight. AI does not eliminate cost, it transforms cost. Specifically, it converts labor costs into computational costs. And unlike salaries, which are relatively stable and predictable, computational costs are variable, usage-dependent, and highly sensitive to scale. The implication is profound. Companies are no longer optimizing for headcount efficiency. They are optimizing for compute efficiency. This shifts the competitive landscape from human resource management to infrastructure management. Firms that can access cheaper compute through proprietary data centers, energy advantages, or strategic partnerships gain a structural edge. Moreover, this shift introduces a new form of financial risk. Labor costs are linear and forecastable. Compute costs, by contrast, can escalate rapidly with user growth. A successful AI product does not just generate more revenue, it also generates exponentially higher operating costs. This creates a paradox where scaling can simultaneously drive growth and erode margins. Therefore, the statement that AI may cost more than humans should not be interpreted as a failure of the technology. It is an indication that we are entering a new economic regime, one where intelligence is no longer scarce, but the infrastructure required to deliver it is. To understand the economic implications of AI, we must begin with the perspective of industry insiders. Brian Catanzaro, Vice President of Applied Deep Learning at NVIDIA, has highlighted a critical reality. For advanced AI teams, the cost of running models can exceed the cost of hiring top-tier engineers. This statement reflects direct operational experience, not theoretical speculation. In traditional software development, the primary cost driver is human capital. Engineers write code, deploy systems, and maintain applications. Once the software is built, the marginal cost of serving additional users is relatively low. This is the foundation of the software scales cheaply paradigm that has dominated the tech industry for decades. AI breaks this paradigm. Unlike traditional software, AI systems, especially those based on deep learning, require continuous computation. They are not static assets. They are dynamic systems that consume resources in real time. Every inference request, whether it is a chatbot response or an image recognition task, requires processing power. This processing is typically executed on specialized hardware such as GPUs, which are expensive to acquire and operate. Furthermore, AI systems introduce additional layers of cost that do not exist in conventional software. These include data pipeline management, model retraining, performance monitoring, and safety alignment. Each of these components requires both computational resources and human oversight, creating a hybrid cost structure that is more complex than either pure labor or pure software. The transition from labor-driven to infrastructure-driven cost models has several implications. First, it changes how companies allocate capital. Instead of hiring more employees, firms invest in data centers, cloud services, and long-term compute contracts. Second, it alters the skill sets that are most valuable within organizations. Expertise in distributed systems, hardware optimization, and energy efficiency becomes as important as traditional software engineering. Third, and perhaps most importantly, it redefines scalability. In a labor-driven model, scaling requires hiring more people, which is constrained by talent availability and organizational complexity. In an infrastructure-driven model, scaling requires more compute, which is constrained by capital and energy. This shifts the bottleneck from human resources to physical resources. The broader macroeconomic context reinforces this shift. Global demand for AI compute has surged, leading to supply constraints in GPUs and increased investment in semiconductor manufacturing. This has geopolitical implications, as countries compete for control over critical technology supply chains. In summary, the context provided by industry leaders reveals that AI is not simply a tool for automation. It is a new economic layer that reconfigures how value is created, distributed, and captured. Understanding this context is essential for any organization attempting to adopt AI strategically. To properly evaluate the economics of artificial intelligence, it is necessary to decompose its cost structure into its fundamental components. Unlike traditional labor models, where cost is primarily concentrated in salaries and benefits, AI systems operate through a multi-layered cost architecture. This architecture can be broadly divided into three core elements: training cost, inference cost, and infrastructure cost. The first component, training cost, represents the upfront investment required to build an AI model. For frontier models, this can reach tens or even hundreds of millions of dollars. Training involves processing vast datasets through highly parallelized GPU clusters over extended periods. While significant, this cost is often treated as a one-time or periodic capital expenditure. However, the second component, inference cost, is where the economic dynamics become more complex. Inference refers to the real-time use of a trained model to generate outputs. Every user interaction with an AI system triggers inference. Unlike training, which is episodic, inference is continuous and scales directly with usage. This means that as a product becomes more successful, its operating costs increase proportionally, and in some cases, exponentially, due to latency requirements and redundancy systems. The third component, infrastructure cost, encompasses the physical and operational environment required to support both training and inference. This includes data centers, cooling systems, networking infrastructure, and energy consumption. Modern AI workloads are extremely energy-intensive, and electricity costs alone can represent a significant portion of total expenditure. When compared to human labor, the contrast is stark. Human costs are relatively linear and predictable. A company can forecast salaries, benefits, and productivity with reasonable accuracy. AI costs, by contrast, are highly variable and dependent on usage patterns, system architecture, and external factors such as energy prices. Another critical distinction lies in cost elasticity. In a labor model, reducing costs typically involves reducing headcount, which has immediate operational consequences. In an AI model, costs can be adjusted by optimizing models, reducing inference frequency, or shifting workloads across different hardware configurations. This introduces a new dimension of operational strategy focused on efficiency engineering. The system breakdown also highlights an important misconception, that AI is inherently more efficient than humans. Efficiency in AI is not guaranteed, it is engineered. Achieving cost-effective AI deployment requires careful optimization of model size, latency, accuracy, and resource allocation. Without this optimization, AI systems can easily become cost centers rather than value drivers. In conclusion, understanding the system-level cost structure of AI is essential for informed decision-making. It reveals that AI is not a simple replacement for labor, but a complex operational system with its own economic logic. Companies that fail to grasp this complexity risk misallocating resources and undermining their competitive position. To translate the complexity of AI cost structures into actionable insight, we can formalize a framework that captures the economic transformation currently underway. The traditional business equation can be expressed as follows. Output is generated through a combination of labor and capital, with labor often being the dominant variable cost. In contrast, the AI-driven model shifts this balance significantly. The new equation can be conceptualized as AI business model equals compute cost plus energy cost plus data cost plus residual labor. In this framework, labor does not disappear, but it becomes a secondary component. The primary drivers of cost are computational resources and the infrastructure required to sustain them. This reconfiguration has several strategic implications. First, it introduces capital intensity into domains that were previously labor-intensive. Industries such as customer service, content creation, and even software development are now subject to infrastructure constraints. Companies must invest heavily upfront or commit to long-term operational expenditures through cloud providers. Second, the framework emphasizes the importance of scale. AI systems exhibit economies of scale, but only under certain conditions. Fixed costs, such as model training, can be amortized over large user bases, but variable costs, such as inference, remain sensitive to usage. This creates a dual dynamic where scale can both improve and degrade profitability, depending on how efficiently resources are utilized. Third, the framework highlights the role of data as a cost and a strategic asset. High-quality data is required to train effective models, but acquiring, cleaning, and maintaining this data incurs significant expense. At the same time, proprietary data can create competitive advantages by improving model performance and reducing reliance on external sources. Another important aspect of this framework is risk management. In a labor-based system, risks are associated with hiring, retention, and productivity. In an AI-based system, risks shift toward infrastructure reliability, cost volatility, and technological obsolescence. For example, a sudden increase in energy prices or a disruption in GPU supply can have immediate financial impact. From a managerial perspective, this framework requires a shift in mindset. Decision-makers must move from thinking in terms of headcount optimization to thinking in terms of resource allocation across computational assets. Metrics such as cost per inference, utilization rates, and energy efficiency become critical performance indicators. Ultimately, this framework provides a lens through which to evaluate AI investments. It clarifies that the question is not whether AI is cheaper than humans, but whether the value generated by AI justifies its cost structure. This is a fundamentally different question, and one that requires rigorous analysis rather than assumptions. Empirical evidence is essential to validate theoretical frameworks, and recent research provides important insights into the economic viability of AI automation. A 2024 study conducted by Massachusetts Institute of Technology examined a range of tasks, particularly those involving visual recognition and decision-making, to assess whether AI could replace human labor cost-effectively. The findings are striking. The study concluded that only approximately 23% of the analyzed tasks could be automated by AI in a way that is economically viable. In contrast, for the remaining 77% of tasks, human labor remains the more cost-effective option. This challenges the widespread assumption that AI will lead to broad-based labor displacement in the near term. The reasons behind these findings are multifaceted. First, achieving human-level performance in many tasks requires highly sophisticated models, which in turn demand substantial computational resources. The cost of training and deploying such models often outweighs the savings from reduced labor. Second, AI systems are not perfectly reliable. Errors, edge cases, and unexpected behaviors introduce additional costs in the form of monitoring, correction, and risk mitigation. Another factor is the complexity of real-world environments. Many jobs involve nuanced judgment, contextual understanding, and adaptability, areas where AI still struggles. Replicating these capabilities requires not only advanced algorithms, but also extensive data and continuous retraining, further increasing costs. The study also highlights the importance of task granularity. Rather than replacing entire jobs, AI is more effective at automating specific components of a workflow. This suggests that the future of work is likely to involve hybrid models, where humans and AI collaborate, each handling tasks that align with their respective strengths. From a business perspective, the implications are clear. Companies should not approach AI adoption as an all-or-nothing proposition. Instead, they should conduct detailed cost-benefit analyses at the task level. This involves identifying which processes can be automated economically, and which should remain human-driven. Furthermore, the findings underscore the importance of continuous evaluation. As AI technology evolves, the cost-performance balance may shift, making previously unviable applications feasible. However, this evolution is not guaranteed and may vary significantly across industries and use cases. In summary, the MIT study provides a data-driven perspective on AI economics. It reinforces the idea that while AI has transformative potential, its economic viability is highly context-dependent. Organizations that base their strategies on empirical analysis rather than hype are more likely to achieve sustainable outcomes. To fully grasp the scale of the AI economic transformation, it is necessary to examine the magnitude of current investments. According to industry estimates, global spending on AI infrastructure reached approximately $740 billion in 2024. This figure includes expenditures on data centers, GPUs, networking equipment, and supporting technologies. This level of investment is unprecedented in the history of the technology sector. It reflects not only the perceived potential of AI but also the intense competition among companies and nations to secure a leading position in this domain. However, such massive capital allocation also introduces significant financial pressure. One of the key characteristics of AI investment is its front-loaded nature. Companies must commit substantial resources before realizing any returns. This contrasts with traditional business models, where investments can be more incremental and aligned with revenue growth. The result is increased exposure to financial risk, particularly if expected returns do not materialize. Another important aspect is the variability of operating costs. While capital expenditures can be planned and budgeted, operational expenses associated with AI, such as energy consumption and cloud usage, can fluctuate based on demand. This makes financial forecasting more challenging and requires more sophisticated cost management strategies. The scale of investment also has implications for market structure. Large technology companies with access to capital and infrastructure are better positioned to absorb these costs and achieve economies of scale. Smaller firms, by contrast, may struggle to compete and become dependent on cloud providers or specialized platforms. Additionally, the concentration of investment in AI infrastructure has ripple effects across related industries. Semiconductor manufacturers, energy providers, and construction companies involved in building data centers all benefit from increased demand. This creates a broader economic ecosystem centered around AI. However, the rapid pace of investment also raises concerns about sustainability. Questions have been raised about the environmental impact of large-scale data centers and the long-term viability of current energy consumption patterns. These factors may influence regulatory policies and further affect cost structures. In conclusion, the numerical scale of AI investment underscores the significance of the ongoing transformation. It is not merely a technological shift, but a reallocation of global capital on a massive scale. Understanding these numbers is crucial for assessing both the opportunities and the risks associated with AI adoption. The convergence of high costs, rapid investment, and evolving capabilities creates a paradox that lies at the heart of the AI economy. On one hand, companies are adopting AI to improve efficiency and reduce reliance on human labor. On the other hand, the total cost of operations is increasing rather than decreasing. This paradox is evident in the behavior of major technology firms. Many have implemented significant layoffs, reducing headcount in anticipation of AI-driven productivity gains. At the same time, they are increasing their spending on AI infrastructure and tools. This suggests that cost savings from labor reduction are being offset or even exceeded by increased spending on computation. A concrete example comes from Uber, where the adoption of AI coding tools has reportedly led to higher research and development costs. While these tools may enhance developer productivity, they also introduce additional expenses related to usage, integration, and maintenance. This dynamic highlights a critical misunderstanding. Efficiency gains do not automatically translate into cost reductions. Efficiency can lead to increased output, improved quality, or faster time to market, but it may also require higher levels of investment. In the case of AI, the latter is often true. The implications extend beyond individual companies to the broader labor market. The combination of layoffs and increased capital expenditure reflects a transitional phase in which organizations are restructuring their cost bases. This transition may involve short-term disruptions as companies adjust to new economic realities. For decision-makers, the key takeaway is that AI adoption should be evaluated in terms of value creation rather than cost reduction. The relevant question is not, will AI save money, but will AI generate sufficient value to justify its cost? This requires a more nuanced approach to investment decisions. Another important consideration is competitive dynamics. As more companies invest in AI, the baseline for performance and capability increases. This creates pressure to adopt AI not because it is cost-effective, but because it is necessary to remain competitive. In such scenarios, AI becomes a strategic imperative rather than an optional efficiency tool. In summary, the so what of AI economics is that traditional assumptions about cost and efficiency no longer hold. Companies must adapt their thinking and develop new frameworks for evaluating investments. Those that fail to do so risk being caught between rising costs and intensifying competition. Given the complexity and uncertainty surrounding AI economics, organizations must adopt a structured approach to decision-making. The first step is to move away from generalized assumptions and toward case-specific analysis. Not all AI applications are equally viable, and the economic outcome depends heavily on context. A useful starting point is to categorize AI adoption strategies into three broad options: build, rent, and optimize. The build approach involves developing proprietary models and infrastructure. This offers maximum control and potential competitive advantage, but requires significant capital investment and technical expertise. It is typically feasible only for large organizations or those operating in highly specialized domains. The rent approach involves using third-party APIs and cloud services. This reduces upfront costs and accelerates deployment, but introduces dependency on external providers. Costs are variable and can escalate with usage, making it essential to monitor and manage consumption carefully. The optimize approach focuses on hybrid solutions, such as using smaller models, caching results, or combining AI with rule-based systems. This strategy aims to balance performance and cost, making it particularly relevant for small and medium-sized enterprises, SMEs. In addition to choosing an adoption strategy, organizations must implement robust cost management practices. This includes tracking key metrics such as cost per inference, utilization rates, and return on investment. Without these metrics, it is difficult to assess whether AI initiatives are delivering value. Risk management is another critical component. Companies must consider not only financial risks, but also operational and reputational risks. For example, reliance on AI systems introduces the possibility of errors or biases that can impact customer trust. Mitigating these risks requires ongoing monitoring and governance. Furthermore, decision-makers should adopt a phased approach to AI implementation. Rather than deploying AI across the entire organization, it is often more effective to start with pilot projects and scale based on proven results. This allows for learning and adjustment without exposing the organization to excessive risk. Finally, it is important to align AI initiatives with broader strategic objectives. AI should not be adopted for its own sake, but as a means to achieve specific business goals. This alignment ensures that investments are purposeful and contribute to long-term success. In conclusion, effective decision-making in the AI era requires a combination of analytical rigor, strategic clarity, and operational discipline. Organizations that approach AI with a structured framework are more likely to navigate the complexities and realize its potential. The emergence of artificial intelligence, as a dominant technological force, marks a turning point in the evolution of business economics. What began as a tool for automation has evolved into a foundational layer of modern infrastructure. This transformation requires a fundamental rethinking of how organizations perceive and manage costs. The central insight is that AI is not a replacement for human labor in the traditional sense. It is a new form of capital, one that enables the production and distribution of intelligence at scale. Like any form of capital, it requires investment, maintenance, and strategic management. This perspective helps reconcile the apparent contradiction between rising costs and increasing adoption. Companies are not investing in AI because it is cheaper, but because it offers capabilities that were previously unattainable. These capabilities include real-time data analysis, personalized user experiences, and the ability to operate at global scale. However, these benefits come with significant challenges. The high cost of infrastructure, the complexity of implementation, and the uncertainty of returns all contribute to a risk landscape that is fundamentally different from traditional business models. Navigating this landscape requires new skills, new frameworks, and a willingness to question established assumptions. Looking ahead, several factors will influence the trajectory of AI economics. Advances in hardware and algorithms may reduce costs and improve efficiency. Regulatory developments may impose new constraints or create new opportunities. Market dynamics may shift as new entrants and innovations reshape the competitive landscape. Despite these uncertainties, one thing is clear. AI will continue to play a central role in shaping the future of business. Organizations that understand its economic implications and adapt accordingly will be better positioned to succeed. Those that rely on outdated assumptions risk falling behind. In closing, the question is not whether AI is more expensive than humans. The question is whether organizations can harness AI in a way that creates sustainable value. This requires a shift from viewing AI as a cost-saving tool to recognizing it as a strategic asset. AI is not the new employee. AI is the new factory, and factories by their nature are expensive, but powerful.